Hello, everyone, and thanks for joining us to our session at the end of this intense week. We're going to showcase how at New Relic we manage a multi-cloud Kubernetes infrastructure leveraging cluster API on top of a cell architecture in order to scale out workloads, but also while limiting the blast radius for incidents. My name is Javier Mosquera Sanchez. I'm working as a principal software engineer. I'm a Kubernetes and multi-cloud architect at New Relic, and I'm joined at the stage by my colleague Tasdik.
Hey, I'm Tasdik, and I work as a senior software engineer at New Relic in the same team as Javi.
Cool. So we'll start outlining some context, some numbers about our scale, the problem that we want to solve. Also, why we moved to a cellular architecture, leveraging also cluster API in order to implement this Kubernetes infrastructure in multiple cloud providers. Additionally, we are going to showcase how we added some abstraction layers on top of this to ease the consumption for instances and the different offerings and nuances that the cloud providers offer us. Now, what we do at New Relic? We provide an intelligent observability platform that empowers developers to enhance digital experiences. We have more than 85,000 active customers, and we process more than 400 million queries per day. We ingest around 7 petabytes per day. That makes, at the end of the year, around 3 exabytes. And with that, we process 12 billion of events per minute. Now, how does this translate into Kubernetes? So we operate all of this on top of 280 Kubernetes clusters. We run more than 5,000 pods on over the 21,000 nodes. And we run all of this in multiple cloud providers in multiple regions. And our average cluster has between 300 and 500 nodes. And we run on top of them, on each of our clusters, around 5,000 and 7,000 pods.
Now, at a high level, our architecture ingests and processes telemetry data from our customers that they send us, instrumenting their applications and their infrastructure, leveraging our agents. This could be done through language agents, infrastructure agents, cloud integrations, etc. So for ingest, data flows through HTTP endpoints exposed via CDNs and gets ingested and processed through specific data pipelines depending on each data type, preparing it for storage in our distributed New Relic database, but also going into a hot path for triggering alert notifications. For the query path, customers query this stored data leveraging our UIs and APIs, also exposed through a CDN.
Now, the problem context about all of this is that for many years, we were running most of our services into a containerized workloads, but running on top of a DCOS, single DCOS cluster. And regarding our data pipelines, they leverage Kafka. We are heavy Kafka users. And we were running also a unique Kafka clusters in order to accomplish that. Because of this kind of monolithic infrastructure, it was very hard to scale, update. So any operation regarding adding nodes or upgrading, it could be very risky. Frequently, we were running into incidents with a huge blast radius. Basically, when we have an incident on this, we were affecting all of our customers, right? So at some point, we started to solve the problem, started thinking about solving the problem. So we initiated, back in 2020, a program, a multi-year program, in order to first migrate to the cloud, in order to have more scalability capabilities, but also we wanted to isolate the blast radius, to limit the blast radius in case of incidents. So we also aligned this program to shift to a cell-based architecture. Now, which are cells, basically? In a biological context, a cell is the smallest unit that can live on its own. So in order to accomplish that, it should have all the resources inside, all the components necessary for accomplish a specific function, right? It should be independent, let's say. Another characteristic is that they exchange energy and matter. So effectively, the cells are interconnected each other in order to provide more complex functions, right? Now, talking about a cell-based architecture, this architecture aligns with this definition regarding cells because a workload in this architecture is decomposed in self-contained installations that should satisfy operations for a shard. So when we talk about a shard, we are talking about a subset of a larger data set. For instance, a subset of our users, right? So this makes a cell an independent unit of scale. It's also limit the blast radius because if you have an issue on a cell, that's limited to that specific cell, so in consequence, it's limited to a specific subset of your data, right? And in order to scale out, as this is a repeatable pattern, what you need to add is more cell instances for that workload. And that's kind of one of the hardest parts because of this architecture, because you need to find out a logic, a thin layer you put over the cells in order to shard that traffic between the cells. You need to shard the data. You need to manage that traffic flowing to the different cell instances. So that makes the cell router. And as we were talking about workloads, you need to identify, decompose your infrastructure into those isolated, repeatable patterns. That's also a critical moment for going to a cell-based architecture because you need to kind of implement some mechanism that help you on this. For instance, a domain-driven design. So you identify workloads and create new cell types. So that was a kind of generic definition for a cell, right? For us at New Relic, we are implementing cells scope to an AWS account, Azure subscription, or GCP project. So a cell is living in a specific unit of this kind. We added only one Kubernetes cluster inside. We added one Kafka cluster, and we added only one VNet or VPC in order to give the networking for that specific cell instance. Depending on the cell type, we should be adding also some other resources like data stores, load balancer, whatever that cell type needs to work as an isolation and independent unit. Additionally, they are going to be paired with other cell types if they need to exchange information, like the biological cells. And in our case, we deploy it in the multi-availability zone setup. Another special characteristic we added is that we wanted them to be ephemeral. So we wanted them to be destroyed and replaced each time. So we link this with the Kubernetes lifecycle of 90 days or each version. It's something we are still working on it, but it's a characteristic that we want to achieve. And regarding from the previous, for the former diagram, if we are talking about decomposing a monolithic infrastructure in several workloads, it means that you are going to have different cell types. Each cell type, it would be representing a specific domain, right? And also, another important point is that this is a living architecture. It's continuously evolving. Maybe you set up a specific cell type. You determine, oh, this is too big. We are putting too many resources, and you want to decompose that cell type into different, smaller cell types. Now, from our former diagram, this is how it looks, turning it into cells operating, being independent units. And in our case, as we have two different data paths, we need different cell routers with different logic in order to accomplish the share of the data for the ingest, but also for on the query path. Now, this is a picture that I think it represents visually very great the achievement of jumping from a monolithic infrastructure into a cell architecture. This is a snapshot from the first year of our program. Here we are seeing the telemetry data from our customers flowing into our environment. And you can notice that at the beginning, there's this big chunk, blue chunk of data flowing that represents our former data centers. A long time, that chunk is decreasing, while you can notice several smaller chunks of data flow that represent data flowing to specific cell instances. Now, you can see how we were sharing that traffic from our customers into isolated units. Now, this looks cool, but of course, changing from a monolithic infrastructure into a highly distributed environment has a lot of challenge. For instance, the asset management, cell inventory, and Kubernetes cluster lifecycle. If we were talking about that we run more than 280 Kubernetes clusters, and each cluster lives inside a cell, it means that we have more than 280 cells, right? Also, we run this in a multi-cloud implementation, so it makes it harder. And because of that and the different compute offering each cloud and the different nuances each cloud provides, we need to put some instruction layers for our internal customers, for our developers, in order to consume all of this in a seamless way. So the scaling offering in an efficient way is very important. Now, why we jump into Cluster API? Why Cluster API? So in order to tackle some of these challenges, Cluster API, it helps us with the lifecycle of the management of clusters, right? It gives you the abstractions to do this in a multi-cloud environment. It gives you the declarative specification, so you run and operate Kubernetes managing other Kubernetes. And also, you can streamline in a seamless, coherent operational way from a centralized point to any cloud, to any infrastructure. Now, here, again, we made it slightly different. We have what we call a command and control cluster, where we extended the Kubernetes API, and we create CRDs that model our cellular architecture in order to manage the lifecycle of cells. But also, of course, we run and bootstrap the lifecycle management of Kubernetes. We bootstrap the Kubernetes from here. We have a streamlined bootstrapping process that helps us doing the same way for any cloud. Now, the different thing that we did here is that as we want the cells to be isolated units, what we determine is to, after the bootstrapping process, we move the management copy objects into each destination cluster. So each each targeted cluster, each worker cluster is at the same time a control plane, a management cluster and worker cluster at the same time. We made it isolated, while we maintain a centralized point in order to streamline operations, let's say. And with that, I'll hand over to my colleague, Tasdik, to go deeper.
Thanks, Javi. Given the numerous moving parts and teams involved and the frequency in which we were creating and decommissioning a cell, we need a solid, repeatable, and reliable way to maintain and decommission KRS clusters. So this process also needs to be easy to debug, maintain, and extend. And we should also be able to checkpoint the various states. Let's see how do we do this on a very high level. We have a command and control cell, which operates by running different homegrown cluster controllers, which in turn monitors the creation of a homegrown cluster CRD object, which gets created after the prerequisite cell build automation gets run. Once this object is created, the cluster controller specific to the cloud provider manages the reconciliation. And during this reconciliation process, the K-test job is initiated that creates a kind cluster in Docker mode. This client cluster is used to install CAPI and the CAPI cloud provider installation and necessary cluster dependencies. These objects and necessary cluster dependencies, which objects require to create we also create the objects required to create the control plane and some initial worker nodes. Finally, these resulting objects are transferred to the target K-test cluster, facilitating self-management of the cluster by itself, and the reconciliation continues further. Let's take the example of Azure Cloud Provider and its bootstrapping process. On the very left side, you will notice that we install inside the kind cluster, which is running inside the K-test job, the CAPI and CAPZ controller, and after that, we create the kubeadm control plane object to create the control plane. Machine deployments are also created to house applications which are deployed during the cluster bootstrapping process. And once the control plane is ready, we start installing cluster dependencies. This is followed by a clusterctl init on the target K-test cluster to deploy the necessary controllers and CRDs for CAPI and CAPZ. Subsequently, a clusterctl move operation is executed to make the target cluster self-managed, along with all the dependencies which were installed. The K-test job concludes, allowing reconciliation to proceed further with additional cluster operations like syncing waves of Argo applications in order to make the cluster ready, running finally a set of test suits from our side to make sure the cluster is ready to receive live deployments from teams. Also noted here are the groupings of different CAPI and CAPZ objects which are required to create the control plane and the worker nodes. For other cloud providers like AWS and GCP, the same process is followed for bootstrapping, with the difference being that the control plane could either be hosted or self-managed. Now that the control plane is ready, we would want the developers to start using the cell. Let's take a look at how developers provision nodes for their applications. We leverage machine pools very heavily for this, which is the primary underlying construct exposed to developers for creation and management of K-test nodes. Since this would be a very frequent operation, we would want to get out of the way of developers as much as we can in the process of creation of machine pools. And for this, what we have done is we have exposed a generic machine pool Helm chart, which the developers use to create an Argo application deployed via our internal deployment platform in the target cells. Now, as this Argo application is deployed, underneath, the Helm chart is templated with a mix of global Helm values and sane defaults injected via our K-test webhook to create the necessary objects for node creation with the features requested by the developer in the cloud providers. As users create these machine pools for their applications, let's talk a little bit about the high-level overview of nodes in each cell. Take, for example, in AWS cell here, we have different groups of nodes. We have the general pool, which is multi-tenant for teams to use, and a user application will land here by default if they don't specify any special requirements for their node. Dedicated pools are created by teams when they want specific node features present, which are not present in the general pool, or when they don't want to be affected by noisy neighbors by getting deployed to the general pool. Pools are also differentiated by the node feature of the architecture. When teams want their applications to land up on a specific architecture is when we allow them to use the machine pool chart to simply create a node or a group of nodes with the specific architecture intended by them. Now, you might notice that nodes in each of these pools are provided by two compute providers, CAPI and Carpenter. Carpenter being more efficient in bin packing of application pods inside nodes, utilizing groupless autoscaling and optimizing for cost by trying to find the cheapest node to run from the provided configuration at any given point. As of now, we only have Carpenter nodes in AWS cells, and we will be expanding it further to the other cloud providers. Now that we have created the control plane for the K-test cluster and the necessary node automation creation process is in place for developers to start creating their nodes, let's take a deeper look at scheduling workloads to these nodes. To shed some more light, with the increasing adoption of Kubernetes, we observed a growing variety of scheduling requirements among different teams and applications, which made it hard to track off and ultimately impaired our ability to introduce changes to the underlying compute platform in a safe and agile manner. Our team aims to solve this issue with scheduling classes, a new Relic-specific construct, which our team provides to all users running on Kubernetes. And what is it? It's a declarative way to express scheduling requirements for applications without the user knowing all the necessary node labels and taints which the nodes have. And how does it work? At the heart of it, it's an admission controller in the form of a mutating webhook running on specific resources inside the cell. And some of the design goals which we had in mind was this should be cloud agnostic, given that we run on multiple clouds, and it should not be reinventing the wheel and should build on top of the K8s primitives, scheduling primitives provided by K8s, should have same defaults, deterministic, and users should be able to chain these scheduling classes on top of each other so as to get multiple outputs. On a very high level, when a user deploys an application, the webhook runs its validation. If it needs to do any mutation, and if a mutation is required to be done, the application gets mutated with affinity and tolerations. Once this application has this affinity and tolerations, the K8s scheduler takes over and then tries finding the best node to schedule the pods for the application. And this construct allows us to also run Carpenter as well as machine pools together on the same cell. For example, take this application which is trying to pass feature foo as a requirement via scheduling class. Our scheduling class engine then defaults to Carpenter scheduling class if it's an AWS cell, since the user hasn't mentioned opting out of it. The scheduling class webhooks then add the required affinity and tolerations, and then the K8s scheduler just takes it over from there to schedule it to a Carpenter node created by the node pool configuration which is present inside the cell. Similarly, when the application specifies the scheduling class to opt out of Carpenter, they specify copy as the scheduling class annotation, and then the required scheduling constraints get added, which would make the scheduler schedule the application in a copy pool. Now, as part of streamlining the upgrade process and management of control planes, each cell has its own Argo CD application where all the related control plane objects are managed. We have a homegrown CRD called Cluster Lifecycle, which targets groups of cells based on environment labels which the custom cluster CRD object is tracking. As we change the K8s version on this cluster lifecycle CRD, one of our command and control controllers reconcile on this object, introducing a diff in the K8s version attributes of the upstream objects of KubeADM control plane object, for example, and then the upstream controllers take over the reconciliation and upgrade process. Similar to the control plane upgrade standardization, we also need to do node refreshes inside our K8s clusters, which could be due to a variety of reasons, and not limited to node upgrades, but also patches. And what we do is our two compute providers are Cluster API and Carpenter in general inside all our cells. And to do upgrades, what we do is we have a worker configuration CRD, which tracks attributes like AMI version inside each cell. And what we have done is we have standardized on top of CAPI and CAPI cloud provider APIs, where we enable drift on top of objects of machine deployments, AWS machine pools. We also further build on top of the Carpenter's node drift feature to not redo what Carpenter already allows us to do by default out of the box. We have been running this setup for several years and adding improving features to it. Here are a couple of things which we learned, which we would like to share. Different CAPI cloud provider implementations have different versions of CAPI referenced, and this is hard to manage. On top of managing forks for some bespoke features and fixes, which we manage, and the challenge of keeping this fork synced with upstream is definitely not an easy task. This also brings us to the point of how it's challenging to maintain the automation when different clusters are using different API versions of CAPI and its cloud provider objects. When it comes to self-managed and hosted, on self-hosted clusters, it's easier to maintain the K8s version parity since you can control the upgrade cadence, whereas in a hosted provider, you are tied to the upgrade charter of the vendor, which is different across the vendors, making it, again, hard to be on the same version across different cloud providers. And this becomes especially challenging if you have components which require a specific version of the K8s version deployed across these different cells. So you can feel how challenging this can get over time. There's also lesser control on the management of the control plane components in a vendor environment. For example, if you wanted to pre-warm the control plane components, this operation would simply not be possible in some situations. And the flexibility that is provided when you're hosting the control plane yourself, you can pre-warm depending on when you want to shift the traffic inside a cell almost before the traffic shift is happening, right? So this is something which you can control pretty much by yourself. More standardization of automation is also possible when the clusters are managed by kubeadm managed clusters across cloud providers, because the APIs are simply standardized and you are not building on top of cloud provider specific APIs, which would mean that you have to manage and maintain them differently, bespoke solutions across these cloud providers. So you have chances of more automation and more standardization. The caveat here being that if you're on self-hosted, you are signing up for more work, which would otherwise be taken care of by the cloud provider. For example, if you wanted to do backups, etcd management, and so on and so forth. Furthermore, we wanted to just also add about a little bit on our Carpenter adoption. We have benefited from its groupless auto-scaling feature, it automatically handling insufficient capacity errors, and its ability to do efficient bin packing. It also allows us to it also chooses the cheapest node possible from a set of configuration which we provide in each cell, and to keep the costs low. In cases when the teams are not able to handle the consolidation rate of Carpenter, we allow them to opt out via our scheduling class construct, and they can easily opt out, balancing the act of reliability with cost management at the same time. We plan to further expand on Carpenter on the other cloud providers, and this is something which we want to do in future. With that, thanks, and we would love to hear questions from you and take them.
After we miss this, we would like to mention that there's a tag contributor strategy launching a new mentorship program. So if you are interested in mentoring people from underrepresented groups, please sign up.
Okay, hi.
Hey.
I very much appreciated the talk. It was an eye-opener for me. I have plenty of questions, but maybe two of them now. You talked about this bootstrapper component in the management cluster. What is behind that?
You mean the bootstrapping of the K8s cluster?
Well, the stuff you have to do before you can initialize cluster API, I guess it is. It was like in the middle of your graph.
All right. So during the cell build process, there are a couple of initialization steps inside the account of the cloud provider which we need to do. This is dependent on what type of cell it is and what the requirement of that cell is. As Javi mentioned, there are different cell types. We have a variety of cell types, and we need certain things to be there before even the initialization of the K8s cluster and the reconciliation process starts. So, I mean, to summarize, I think it depends on what cloud provider it is and what cell type it is and what is the use of that cell type. Because depending on that, there are other teams which try doing a lot of other things before this.
For example, AWS, what is the technology behind that? Is it like your own controller? Is it, I don't know, Crossplane, Terraform?
This is homegrown, yeah.
Oh, okay.
You mean before what we do the K8s bootstrapping? I think you were asking what we do before. That's homegrown, yeah.
Okay.
Yeah.
Okay. Any other questions? And you do cluster cuddle move of the Carpi resources, the Kappa resources into the workload cluster. Do you do that for any other resources as well? Like, do you modify cluster cuddle move to extend it, make it move even more custom resources, such as cluster lifecycle configuration or something?
So when we do the cluster CTL move operation, everything which has, so there are two steps to reconciliation. One thing which I didn't mention too much due to this lack of time was during the checkpoint process of K8s cluster creation and the point at which the job succeeds, right? There is another phase where reconciliation of other steps start happening via the command and control cell controllers. But just before the move operation, we have everything which is then required, for example, say the cluster API and the cloud provider installation, and the necessary things which we deem necessary for the cluster to function at this point, and reconciliation to start happening furthermore. All those objects are moved away and moved to the target cell, and the job concludes. So at this point, that one checkpoint has finished, and the next checkpoint starts over, if that makes sense. And we track this inside a specific CRD, which we have on the different states which the cluster build processes in this point. I don't know if that answers your question.
No, that's fine. Thank you very much.
No problem.
Hello there. From what I understood, a cell is declared to be ephemeral. If you don't have control about which application is running in the cell, how do you migrate data if a cell vanishes and a new one is created?
That's a good question. So, and that's a tough one. Actually, well, you control which are the applications, the services that you're going to deploy in that cell, because you need to define that cell type. Now, it could be a stateless cell type. That's the best option, right? And then you don't need to worry about that. But in our case, we first, during the journey, we have some stateful cells. We put some automation tooling for when it was the point to decommission that cell and migrate the data to another cell. We put some automation to do that. That's tough. So along the way, and this is, across several iterations, you try to decouple that stateful part into a different specific cell. And maybe instead being ephemeral, you can put it in a more stateful permanent cell. For us, we have some special cells, we call them enclave. We made them very resilient in terms of few moving components, let's say, instead of having a huge amount of services running there. But basically, yeah, we're taking out that stateful to another cell type. And then we make the original cell more stateless. And that way, when it comes to decommissioning, build new cells, it's easier.
Thank you.
It's not an answer that fits any situation, so you need to take your answers along the way. It's the same with the cell router. So how do you do the cell router? It depends on your workloads and your traffic characteristics, let's say.
Thank you.
Is this on? Okay. Hi. That was my question, actually. I was going to ask if you could explain a little bit more about how your cell routing works, because, I mean, I don't know if I understood this properly, but it seems like, how do you decide when a user hits your API which cell they should be routed to if each cell owns their own data?
Can you repeat a bit with more volume? Sorry, I can't.
Yeah, sorry. So when a user hits your API,
yep.
How do you decide? Could you just talk a little bit more about how the cell routing works? Like, how do you decide which cell a user request should be directed to?
Cool. About the cell routing, you mean?
Yeah.
Sure. So in our case, we have a mechanism analyzing the headers of traffic from customers based on the data type and on the customer ID and API key. And with that, we decide to which cell we should redirect that traffic coming from our customer, basically. So that means that, for instance, for a specific customer, we are able to shift traffic depending on the data type to different cells. We could have been migrating, routing traffic for metrics for cell A, while we could be redirecting traffic from logs to cell B. And we do that with that tuple of data type and customer ID, in a sense. It could be a presentation on its own, but that's, in a sense, the mechanism.
Thanks. So is that more? Is that like? So if it's done with the user ID, say for example, if you're routing based on user ID or something.
To oversimplify, yes, but it's not a user ID; it's customer ID.
Yeah.
And we do some more operations there, but in a sense, that's the idea.
Yeah. Okay. So I mean, like you have some ID that tells you where it should go. Is that? Does each of the cells like publish what IDs they're responsible for, or do you record it like when?
No, we actually save that on a specific repository, let's say. So when it comes to reach out to that data for the query part, first you need to know regarding that query, where is the data located? It could be in several points, right? And we do that with a specific database internally that saves all those, all that metadata, let's say.
Okay, thank you.
You're welcome. Someone else? Well, thank you a lot.
Thanks.
Thanks.